Hey, so all good now if you're seeing my
Okay.
screen.
Yep.
So first thing it says it wants you to graph this curve, and I don't know how exactly they want you to do it. You can always use Desmos, but when they say 1 to infinity, you got to make it clear that this, this point right here is 1, 1. It does in fact go on forever.
Okay.
Right. So that's part A. If you need a nicer sketch, go ahead and use Desmos. And if there's now I saw there's some words that go along with it. Do we need to actually, do you need me to actually provide any of those words, or?
Just like a brief summary, just to like. Well, I guess not for that one, since that one's just sketching.
Yeah. Now it says sketch a
Is that
separate graph.
is that
That's
that's
one
the
over
graph of 1/x?
X. Yeah. Now what is this Gabriel's horn? Oh, okay. So Gabriel's horn is like a three-dimensional volume thing. So
Yeah,
let
it's in the
me
book.
make one of those here, I guess, for part B.
Let me look in the book and see.
So the like when I see something like this, I see it's gonna have kind of a disc here that goes like that, and then it's got this kind of shape to it. And that's my Gabriel's horn, attempt at a Gabriel's horn.
Okay. Oh, okay, I see what you mean. All right.
All right. So let me know when I can move on to question
Yep.
2.
You're good.
All right. All right. So it says calculate the volume of Gabriel's horn. This is a disk problem, and it's that integral pi r squared dx, and from a to b. But in terms of your problem, you're going from 1 to infinity because those are the limits that it provided in the problem.
Right.
Your r is the 1 over x function squared, because that's the distance of the radius. The radius, from, and if we want to show it in a color up here, like in blue, that's your r. Okay.
Okay.
And then you just work out this integral. So the pi, let me just rewrite this one more time. So it's pi on the outside, 1 to infinity, 1 over x squared dx. Okay. And if that's clear, you just find your antiderivative using power rules. So it's minus 1 over x evaluated from 1 to infinity. Now, I guess we should do the right thing here, which is, let's add in a step. It's the limit as b approaches infinity, pi integral 1 to b, 1 over x squared dx. That comes from this previous line here.
Right, you need to write that part.
Yeah, you have to write it that way. And then it's the limit as b goes to infinity, pi times minus 1 over x from 1 to b. And then I'll bring the pi on the outside. So it's pi limit as b goes to infinity, minus 1 over b plus 1 over 1. And this is where you write your answer of just pi. And you may need some explanation, or you may need to say in words that, I'll type it here. The limit as b goes to infinity, minus 1 over b is 0.
Why do you have to do use like 1 over b in the
I'm putting the value of b in for x at the I'm putting both endpoints in. So like I'm just putting b in for x.
why do you have to do that?
That's the way. So remember, like, let's just say it was 1 to 2. This is a 2, you'd put a 2 here. Do you agree with that?
Right, yep.
So because it's it's really infinity. You can't evaluate it in infinity. You can only evaluate a
Right.
limit. So you put B, you call B is your reference to infinity.
Okay. All right. And which was it disk that we used?
Disk, yeah,
Right. Okay.
disk. I assume you're trying to get this down. So just if anything's unclear, just ask me now. That way you're not
Yeah,
scrambling later.
I just got to refresh. We had spring break too, so it's kind
Good. Did you go anywhere? Do anything fun?
of no, nothing special.
Okay,
Just went to Dallas and saw my dad. Yep.
cool.
Nothing other than that.
You a Cowboys fan?
No, absolutely not.
Okay. We'll try another state team from the state.
Yeah, I'm from Louisiana originally, so
Okay.
Saints fan over here.
Okay. Well, you might get Deshaun Watson, I guess. But,
Hope so.
If that all works out.
Hope so. I'm ready to move on, brother.
Okay. Yeah. Always let me know.
Right.
All right. So now, the next question here is to find the surface area. Okay.
Right.
And surface area is it's like yet another integral formula. Area. So there's like all these integrals. There's like line the length of the line, volume, and this is just another one that you have to have in your book.
Mhm.
Although this is two-dimensional, we're not doing that.
What's the comparison theorem?
Yeah, so the comparison theorem says that there's two cases. There's basically like you compare your curve to somebody else's another curve, and if your curve is either above or below it, it converges or diverges depending on the actual value or actual value, the actual one that curves. I'll draw a picture if you really want to know here, but let me get this down.
Okay. Because it says use the comparison theorem to calculate the surface area. So
yeah, let me show you here. So when you rotate about the x-axis, which is what we just did, your ds is coming up here. Excuse me. Do you want to talk about can we do the comparison theorem another time? Like either after this question or because it's going to really diverge. We're going to diverge from what we're doing.
Yep.
So your y in this problem, your y is 1 over x. Okay.
Right.
And your ds though, your ds is the derivative of this. So your derivative of this, your y prime, put your y prime here. Your y prime is minus 1 over x squared. I mean, that's just power rule. You can look at that. You can see if that makes sense later. But then you need to square it. So it becomes 1 over x to the 4th. Okay. And so why are we doing all that? Because your ds is the square root of 1 plus 1 over x to the 4th.
Right.
And your surface area integral is 2 pi 1 over x square root 1 plus 1 over x to the 4th.
Right.
Dx. And we're going from 1 to infinity. Now I see why this is an issue. Use it to calculate the surface area by comparing the surface area formula to the integral. So this is not calculable as far as I know. Let me do a quick search to make sure I'm Gabriel's horn.
All right.
But then I think that's why. So we may have to actually do this. Okay, so we're good on that.
Yeah, I'm good.
Okay, so you got that. All right. So here we actually do have to do this comparison thing. So let me try to draw some graphs here. So and actually, maybe I'll do it in Desmos and snip them in so that you've got a better look here. So let me graph y equals 1 over x squared, and we're going to go from 1 x greater than or equal to 1. All right. Let me just, I guess I'll just do it for the one here. So that we're doing. So let me just I'm just going to graph this one and I'll snip it in. So we have the square root of 1 plus 1 over x to the 4th. Does that look right? Yes. Okay. All right. So let me grab this, snip it in, get rid of this. All right. Okay, so here we go. Got it snipped in here. All right. So the red curve is 1 over x. Do you see that?
Sorry. Yep, that's it.
Yeah. Okay, so red curve is 1 over x. Blue curve is the other one, 1 over x times square root 1 plus 1 over x to the 4th. And I only graphed it from 1 to infinity to illustrate this. Okay, so the blue, do you see that the blue is always above the red,
Yeah.
at least in the beginning? And then like I could zoom in here and show you that it's always above the red.
Mhm.
So why does this matter? So you're getting into this part of the course where you talk about these things called converges or diverges. So the integral 1 over x from a to infinity dx, this always diverges. Okay.
Mhm.
Now, because it diverges, and it's the red one, and since the blue is above the red, it also diverges.
Okay.
So the way kind of I show this is if I give you a curve and I say, okay, this one diverges.
Mhm.
If you have another curve above it, if you have a curve, any curve above it here, it also diverges.
Is it different for if it's below it?
It's unknown
Oh,
at the
okay.
moment. So then we get to, let me draw the other one. So the other scenario is I give you a curve and I tell you this thing converges. If it's below it, it also converges.
Okay.
But if it's above it, don't know.
Okay.
Okay.
Mhm.
So you're looking for some words to go along with what I just said here. And this graph, you have to include a graph like this. And you want to include that this thing always diverges. And you want some words that say, since 1 over x square root 1 plus 1 over x to the 4th is always greater than 1 over x, if integral 1 to infinity 1 over x dx diverges, which is known to be true, then so does integral 1 to infinity 1 over x square root 1 plus 1 over x to the 4th dx.
Okay, that's like coming from the comparison theorem.
Yes, that is the
Okay.
comparison theorem. What I showed down here in these graphs is the comparison theorem, but you have to write out a statement like
Right.
this. And some instructors are really picky they actually want you to say things like a of n, b of n. Since a of n is greater than b of n, since the integral a of n converges, diverges, then b of n also. And I don't know
So,
what your instructor wants here, so just be careful.
so would the surface area be infinity?
It is unknown. So it is not infinity, it is unknown.
Okay,
Diverges
why is
means
that?
we cannot calculate it. It is an unknown value.
Oh, I thought since when you usually get like something is diverging, you get infinity out of the answer, or it like goes to infinity, goes to negative infinity or something.
It so this is really a gray area of math, and for
Mhm.
me, because like infinity is this destination, and if we had lots of time, I think I could show you somewhere where you could see that the sequence or the integral, it doesn't go to infinity because it goes to like a number less than one. We just don't know
Uh-huh.
what it is.
Uh-huh.
And the problem is like this is really mathy. Like, and you do it for a little bit and then you get away from it. Um,
Uh-huh.
what you have to take away from this for the project is some of what I wrote here, but more generally, it's these pictures. Like,
Right.
if you get a question where you see that something diverges and the other one's above it, then it also diverges. Like that's your main takeaway here.
Right. Okay.
In terms of like what it actually is, it is unknown. Like if we go back to like
Yeah,
what we
to
can't,
calculate surface area.
you want to say that you like we cannot calculate the surface area because it diverges, and that's
Right.
now you could say diverges to infinity. That would be okay, but I would not say that the surface area is infinity.
Diverges to infinity
Right.
would work. Is that why in the next question, number 4, is that why it's asking explain why some might view it as a paradox?
So the paradox is, why can you calculate the volume but not the surface area?
Oh, okay.
And that, yes, that is, I guess that is a paradox. I'll leave that for an English class, but there are other things like this where, and the paradox truly is, and I'll type it here. Because if I give you any other three-dimensional object and I say, what is its volume and what is its surface area, you could give me a number. But for some reason, this one you can't.
Uh-huh. And is that it? That's it for just number 4?
Well, I would write more than this. I would maybe, I think when to me, when an instructor does this, they want you to actually go find a resource
Uh-huh.
and like look at it, read it, and then cite it, and
Okay.
give your opinion on it.
Yeah.
Maybe like maybe it bothers you, like it bothers me, is because I'm looking at a cup here, bottle, water. Like why? I can tell you much. I can tell you its surface area. I can look at it, but for
You
some reason
can.
with this, it's because it goes on forever, because the horn actually goes on forever.
Right.
And then you might want to ask, this would be, I don't know if your instructor actually reads this, you might ask or pose the question like, um, are there objects with known surface area but unknown volume? So kind of the reverse of this.
Okay. Do we know the answer to that?
I don't know.
Okay.
You can, I mean, I don't, this is, and that's maybe this horn is the only one.
Right.
Let me see here. You could also use words like, instead of known, you could use words like finite or fixed. volume, but infinite surface area. And I don't really like that use of the word infinite, but that may be the only option.
Now for when we were working out the volume for the,
Yes.
could you write like little notes on this, like for steps, for each step, or so I know?
So right here.
Yeah, so I kind of
Okay.
get, because I have to write every single step out in a
Okay.
sentence.
Yeah, let me just redo it because that will help here. So I'll keep the work on the left. So the integral, it's pi r of x dx from a to b. This is the disk method formula. Okay, and then the next thing we did here is we substitute, or you can even use the word like evaluate for a equals 1, b equals infinity, r of x equals 1 over x. So pi 1 over x. Yeah, I guess that's squared, sorry. Squared dx. And then from here we did some simplifying or rearranging.
Right.
So pi integral 1 over infinity 1 over x squared dx. And then we used a limiting approach. So we said the limit as b goes to infinity, pi integral 1 to b 1 over x squared dx. Okay, so then we determined the antiderivative. Limit as b goes to infinity, pi minus 1 over x evaluated from 1 to b. Evaluate for both endpoints. So that's the limit as b goes to infinity, pi minus 1 over b minus 1 over 1. Maybe substitute, I don't know, the wording probably doesn't matter. So you end up getting pi 0 minus or 0 plus 1 when you evaluate. Maybe change that to simplify. So you get pi when you simplify here.
Alrighty. Now, why did you need to like take a limit of it?
You're not allowed in like proper form to just put infinity in because it's an improper integral, I guess is probably the right wording. Proper integral. Maybe that goes down here. Use the limiting approach because it's an improper integral.
Is it an improper integral just because it goes to infinity?
Yes.
Okay. Okay, that makes sense. All right. That's really it for the project.
Great.
But I do have a quiz tomorrow, so let's. It's over sequences.
Okay. Why don't you send over what you want to work on? I'm just going to take a 30-second refresher here. I got to actually turn some lights on and stuff, but I'll be right back.
All right.
All right, I'm back. Let me know what you want to work on. We can look
All
at some
right,
problems together.
I need to look at. She posts homework problems, so I'm just gonna grab those. Okay, all right, I'm sending it to you right now.
Sounds good. All right, looks like some you said some problems here in 8.1. Determine whether the sequence converges or diverges. Yeah.
She assigned number like number 3 to number 6, and then 8 through 12, and then
Okay.
14 through 20.
Sounds good. I'd like to start with like something like 10,
Okay,
if that's okay.
that works.
All right, let me make sure I got this here. Nothing's gone easy. There it is. All right, so you see number 10 on my screen here.
Yep.
All right, so they said the instructions say determine whether the sequence converges or diverges. If it converges, find the limit. Now, you're dealing with the sequence, which is not the integral, it's not the sum, it's the
Right.
sequence. It's like literally like does it approach a value? And your answer to this is well, based on kind of like treating it like it's a function. If this were f of x equals x cubed over x cubed plus 1, and I said what is the horizontal asymptote, or the same question is what is the end behavior? You would tell me, well, the degree of the numerator is the same as the degree of the denominator, so the end behavior is the ratio of the leading terms. So in this case, like if you were to graph this thing, you would see that it goes to y equals 1 over 1. Like there's a horizontal line there, and it approaches it. Okay, and that's kind of the same thing you're doing over here. The limit as n goes to infinity, n cubed over n cubed plus 1. When you get a really large number and you cube it, then you get a really large number and you cube it and add 1 to it, that 1 is insignificant. And if that's unclear, think of a billionaire or a trillionaire or someone with like a huge amount of money. And if someone with a huge amount of money, does one more dollar really matter to them? No, they're exactly the same. But the analogous problem is the horizontal asymptote. So there's not really any work here. There's not like, oh, let me put some numbers in. You could like to kind of see what happens, but you'll find that you're going to kind of eyeball it
Right.
when you do that. So
So like plug it in infinity and for both ends, and then those two
that
canceling out.
yes,
You get
yes,
1/1.
yes. So like 11 is a good problem to do. Again, like the analogous problem would be, what is the graph of 3 plus 5x squared over x plus x squared? What does it look like? And the answer is that the 3 on the top and the x, they don't contribute as much as the x squared, 5x squared, and the x squared.
Mhm.
Okay, so like as this thing grows, these are irrelevant. So it's approximately 5x squared over x squared. Those cancel, and the answer is that it approaches 5. Okay, and this one has a horizontal asymptote at y equals 5. Now the problem you're doing, it's the same thing. You could literally plug numbers in, but you have to plug in big enough numbers. So like sometimes when students have a calculator, like I actually say, okay, type in n equals 10,000 and like plug it in and see what you get. But again, those don't matter. This is what matters. These are called the power terms, are the ones that like actually matter.
So just the higher, whichever terms like have the higher power in them in the
Yes,
whole equation, just use those and just forget about
yes,
the other ones.
yes. But that only works for these because these are rational.
Uh-huh.
So if I grab one that's not like that, like if we look at 9, see how this one doesn't have,
Right.
you have to figure out like what's going to happen here.
Uh-huh.
So sometimes you got to do what I call a rewrite. And a rewrite here is that this is really 1 over, or I'm sorry, 1 minus, and then 0.2 is really 2 over 10, which is 1/5. And
Mhm.
1/5 to the power of n is really 1 to the n over 5 to the n. And then 1 to the n is always 1. So it's 1 over 5 to the n. So you've got to know all this stuff to be able to answer this question.
Uh-huh.
And then, okay, well, what happens? Well, when n goes to infinity, what happens to 5 to the n? What is 5 to the infinity? Well, it's huge, right? It's a
Mhm.
huge number, but it's 1 over that huge number.
So it's just going up to 1.
Well, 1 over huge number, 1 over infinity is really 0.
Oh yeah, right.
So it's 1 minus this, 1 minus 0. So it ends up equaling 1.
Right, okay.
Now I've done a bad job like so far. Like the first one converges. 10 converges to 1. 11 also converges to 5. And what I would do as a student is I would pay attention to like what is the instructor writing down? Like, are they just doing a lot of talking and then they write down the answer? Because there's not a lot here to do in terms of work.
Mhm.
This one, there's a few more steps. It does converge.
What would be an example of one that diverges?
All right, let's look at one of those here. So that is number 12. So number 12, if I were to graph this, f of x, if I say, okay, f of x is x cubed over x plus 1, we did this thing in pre-calculus, or that is a pre-calculus topic where you say, okay, if the degree of the numerator is greater than the degree of the denominator, it has what's called a horizontal asymptote, but that just means the function diverges. So because this cube is bigger than this x to the 1, this thing diverges. So same here. The cube is going to grow a lot faster than the power of 1. So
Right.
there's a remembrance of like, what did you do in pre-calculus when you learned about horizontal asymptotes?
Right.
Or in the beginning of calculus when you're doing infinite limits, because you're saying, oh, well, this grows really fast compared to this on the bottom, so this diverges. Notice I don't say diverges to infinity, I just say diverges. And that's kind of what the instructors are looking for. They're just looking for like, true, false, diverge, converge kind
Okay.
of thing. Okay, so let's look at 14. A lot of these require a rewrite to be able to be done properly, and this is an example of one. So the numerator can be rewritten like this. Okay, so when the bases are the same, you add the exponents. So that's why they're added here.
Right.
Okay, so this becomes 9 because 3 squared is 9, and then you have 3 to the n over 5 to the n, which can be rewritten as 3 over 5 to the power of n.
Okay.
Now, why does this matter? This is what's called a geometric series. And this is the first one they'll remind you of. The geometric series has what's called a constant ratio. And if that constant ratio is less than 1, this ratio is 3/5. The ratio here is 3/5. It's less than 1, then it converges. Okay. But in terms of like what you're doing, like, do you see how the bottom gets bigger than the top? Like 3 to the
Yeah.
n is less than 5 to the n. So as n goes to infinity, this 5 to the n is going to be bigger than this 3 to the n.
Right.
So it's going to be like, it's kind of the equivalent of like 1 over infinity, because eventually this bottom number is way bigger than the top number.
Right.
And that's 0. So this thing, even though it starts at 9, it's really 9 times 0. So it becomes 0.
Converges to 0.
Converges to 0. And like I'm giving you the answer here and we're working through it, but I don't really know what the instructor will accept, because we're kind of talking about it, not mathing it. We're not giving, symbolic answer representations here.
I mean, you're getting the answer, huh?
Yeah, but please, what I'm trying to say is like ask your instructor what they want, or like really try to
Well,
focus on
what would be an example of like, what do you mean by like the symbolic version or whatever?
Well, like what I'm saying is you can't just like I would, like me personally, I would just write that. I just write goes to 0 and be done. Like I think you've got to show some.
Oh, you wouldn't like even show
No.
Oh, okay.
I'd be
Well,
like,
yeah.
oh, like just goes to 0. And I would do the same thing. And at this one, I just say, oh, it goes to infinity. Like this goes to 1. I wouldn't, there's no work,
Right.
is what I'm trying to say.
Yeah, you have to show work.
How do you show work?
Yeah, you have to show work
So
with her.
Be careful. And it's not because I'm like lazy, or it's really, it depends on the instructor what they want here.
Right.
You have to do 16 or
4, yeah.
all right. So there's this property of limits that if you take the limit as n goes to infinity square root of an, this equals the square root of as the limit goes to infinity an. So why is that useful here? Because you ignore the square root for the moment. You just take the limit as n goes to infinity of n plus 1 over 9n plus 1. And then once you figure that out, you take a square root of it. So this inside here, it's like one of those early ones we did where the degree of the numerator is the same as the degree of the denominator. So this inside part becomes 1 over 9, and then you take the square root of that, and you get 1/3.
All right.
So you may want to go back and review all those limit properties from section chapter 2 or 3, or wherever they were. What else do you want to look at here?
I don't think I need to list the first 6 terms or whatever. That's pretty easy.
You just put the number in for n as 1, and then 2, and then 3, and just simplify.
What about 22 and 23? What are those?
Right.
So
So
actually 8 through 12. What's
we I thought we hit
Did we
most
already
of
do that?
those. We hit most of 8 through 12. 9, 10, 11, 12. We did not do 8. Do you want me to go back and grab 8? 8 is
Yeah,
find a
do
formula.
5 through 8.
Sure. Let me do 6 because you'll have the formula in the back for 5, if that's okay. We can come back to 5 here in a
Okay.
little bit.
Because we did some in class, we did some general formula,
Yeah.
find the general formula.
These are tough. There's no real math here unless they tell you like, oh, this is a geometric sequence or this is an arithmetic or it's recursive. What I look for is like ratios. So what is the ratio between terms? And that's usually a giveaway here. So like -1/3 over 1, is that the same as 1/9 over -1/3? Is that the same as -1 over 27 over 1/9? Is that the same as 1 over 81 over -1 over 27? And the answer is yes, they are. These are all actually -1/3. You can verify that if you want. You have to multiply by the reciprocal, but you will see that they're always that, and that is your R. So for geometric sequences, your AN equals A1 R to the n-1 power. This is for geometric. Geometric have a common ratio, which is what we have here. So A1 is the first term, 1. Your R is -1/3 to the n-1 power.
Okay, we did these by like making a chart with like an n row, a numerator row, and a denominator row,
Okay.
and we would just focus on the numerator, see a pattern between that, and then find it, put it on top, and then find a pattern between the denominators, and then
That does
make
work. I mean,
kind
that
of
does work. It
formula.
depends on the problem, that you're doing
Right.
for that. There are 3 types of sequences. Well, there's actually more than that. The first one is arithmetic, which is what we're about to do. These have a common difference. The second is a geometric. These have a common ratio. And that's important because these are really nice. There are then what are called recursive sequences. And then
I
there
think those
are,
are the ones we're doing, recursive.
and then these are like other formulas, like other basically. So like nice, really arithmetic are really nice, geometric really nice. The other ones are not nice. So like in terms of like if the question just says like, hey, determine the formula, like what I would tell you to do is first be like, all right, well, maybe it's arithmetic. If it's not arithmetic, let me try geometric. If it's not geometric, I will try something else. But this one has a common difference. 8 minus 5, does that equal 11 minus 8? Does that equal 14 minus 11? Does that equal 17 minus 14? And it does. The difference is always 3.
Okay. Oh, okay. I see what you mean.
Okay. Now, just because it has fractions doesn't mean it's going to be geometric. Like I can make a geometric or an arithmetic sequence with a common difference that is a fraction. Like it can always be like subtract 6/7 or subtract 9/8, or like you can mess around with stuff. And there is no like one size fits all thing here. But for an arithmetic sequence, AN equals A1 plus n-1 times D. Your A1 is 5. Your n is your variable and your d is 3. You can simplify this. You actually did this in a previous class, either at this college or at another time when you were taking that.
Where did you get the D? What was that formula that you just?
That was the difference. So I look at the difference between all the terms, and if that's the same, then it's arithmetic.
Is that like a set formula that
Yes, yes.
A1 plus? Okay.
This is for arithmetic.
Oh, okay.
And the other one I did was for geometric. I would study both of those. Like that's what I think. If I were writing a quiz on 8.1, I would give you one arithmetic, one geometric.
Okay.
But there are others. There's so many. There's too many to cover here.
Right.
But this one's 2 plus 3n. All right. So the only other ones you might see are, like these alternating ones, but there's just a lot.
Yeah, we've done that. We've done those a lot.
Is there,
alternating ones?
if, I guess I can do one more problem here or talk if you would like. If you're not, if you got everything you wanted out of today, we can end here, but let
Yeah,
me
let's do
know.
one more.
Okay, what would you like?
Let's see. Let me look. What about? What'd you say about number 5? What did you say about that one?
So yeah, we can do number 5, but 5 and 7 you're gonna have in the back of your book.
Oh, okay.
That's why I
You
was,
just like walk through.
yes. So 5, because there's fractions, I would tend to look towards a geometric. So is 2 over -3, does that equal -4/3 over 2? Does that equal 8/9 over -4/3? Does that equal -16 over 27 over 8/9? And so your answer is yes, it does. You'd have to do a little simplifying, but your R is always -2/3. Okay, and this is geometric. So since it's geometric, you say a(n) equals a1 parentheses r to the n minus 1 power. Your a1 is the first term. So that's -3 times your r, which we just calculated.
And that's the formula for geometric.
Yes.
Okay.
And
We
then
haven't been introduced to that. Those.
that's odd. Because that's only that's what
Maybe
these
we
are.
have. Let me
Yeah.
let me see. No, we haven't. Yeah, we haven't been introduced to those formulas. Introduced, I mean.
All right. Well, I do need to end here. Trenton,
Yeah, okay, that's fine.
thanks for scheduling. I'll send you the notes here shortly, and see you next time.
All righty, thank you.
Have a great night. Bye now.